Okay. Fourth year graduate student in physics, he's going to be presenting his recent single author paper. Take it away.
Hi everyone. Today we talk about planetary rhythms, synchronous circulation on variably irradiated asynchronous planets. So in order to motivate this, I'm sure some of you or many of you might have either read or watched the three-body problem. Without spoiling the plot for you, I'm just going to give you the idea of what goes on. There is a planet in a tri-solar system. It's called tri-solaris. And this planet experiences extreme weather conditions because of the irradiation, varying irradiation it receives. So I'm going to use my title slide as the outline slide as well. So we'll go over variably irradiated planets first, then we'll talk about what circulation means. Then we'll go on to synchronous circulation for synchronous planets, asynchronous planets, and finally the core of the talk, which is about rhythms. So variable irradiation. So as we talked about the three-body problem already, the most generic source of variable irradiation for planets is circumbinary situations where you have two stars at the center instead of one. You can see, look at Kepler 47b, which is Kepler circumbinary planet, and it's irradiation varies with time in this fact. Then you have variable stars. For example, WASP 33b is a hot Jupiter around WASP 33, which is a variable, around Delta Scuti star, which is variable. You can see the transit and secondary eclipses over here. The stars variation signal can also be seen, and then there are gravity darkened stars. So these stars are spinning so fast that the equator is flattened out, and hence it is at a lower temperature than the poles. And if your planet is going in a polar orbit, it experiences varying irradiation as it goes on this orbit. Finally, you have eccentric planets. If your planet is close to the star, you receive a lot of radiation, while away from it, it will not. So for this purpose, it's a theoretical work. We are going to use a very simple form of irradiation variation, which is cosine omega t, where omega is the frequency of radiation. Now let's come to circulation. This is something I do as a part of the Earth atmospheric and planetary physics group in the physics department. For exoplanets, the most basic energy balance is a zero-D model where you have incoming and outgoing energy balanced out, which can give you the equilibrium temperature of the planet, but then you know that it does not hold true for Venus because the greenhouse effect is not incorporated with it. It does not have wind structure. You could go further detailed models like a 1D latitudinal model with insolation radiation across a longitude. But again, there is no wind in this. And then what we use it for in most cases covers different kinds of physics in three-dimensional space, including winds, phase changes for water, and then topography, and chemistry, and all that stuff. But in order to study this problem, we are going to use something which comes at a sweet spot, which is called the 2D shallow water model. It includes more physics than the 0D and 1D models because you can see velocity vectors on it and also look at the temperature distribution. So to motivate this research, previous studies have said that circumbinary planets are as good as the single star planets. So this is a comparison between a single star and a circumbinary planet case, and we can see that the temperature wind maps are almost similar. And this is using a 3D global climate model, which is expensive to run, and hence they have just been able to do it for one planet. So the goal is to do like a more parameter space sweep. So for the shallow water model, we have the momentum and transformation, and I'll just go over terms really quickly. This is the wind term, this is the rotation term, this is our pressure gradient, which drives the flow. But you have something like a dragging effect included in it. And then this is the wind affecting the hydrogen flow. And then this is the radiative forcing. So how is the installation going to affect the flow on the surface of the planet? So as shown previously, this is the time variable component of the radiative forcing with small omega, which is the installation frequency, and capital omega over here represents the diurnal motion of the substellar point. So the substellar point is the point above which the star is directly above the ground or above the planet's surface. And this is the forcing field. So this is the day, this is the substellar point, rise up as cosines on both sides, and these two are night sides. So no forcing over here and forcing on the day side. Synchronous planets, a lot of us already know what tidally locked means. The moon is tidally locked to the Earth, which means the same side of the moon faces the planet at all times. You could have synchronous planets, which would have the same side of the planet facing the star at all times, and this is kind of the substellar point. It has the day side and the night side, and winds going from the day side to the night side. This is the circulation pattern. Basically, took this off from a sphere and plotted it in rectangular coordinates. Interesting thing is that the hotspot, which is the highest temperature location, kind of coincides with the substellar point that is given over here, at least in terms of location along a particular latitude, and it stays fixed to the planet because only one side is being bombarded with radiation, the other side is not. So the hotspot is always on the day side. Coming to asynchronous planets, of course, the Earth is the most common example or relevant example. What we have is a moving substellar point, so it's not being at the same location at all times. And you can see that the blue and the green and the black lines overlap one another. Which means that if you thought of Earth as not being tilted, then the substellar point and the hotspot would just move along with one another. So wherever there is day, the temperature is highest over there, and that is where the substellar point is. So for synchronous planets, substellar point is fixed, while for asynchronous planets, it moves around along particular latitude, the equator over here. So what is synchronous circulation and variably irradiated? Putting all of those things together now, this is an asynchronous planet. So technically, it should have the substellar point going around, just like the Earth. And this is also asynchronous and this is synchronous. So if you apply this particular resonance scenario where capital omega is equal to small omega, which means the installation radiation frequency is the same as the rotation frequency or diurnal period of the planet, you can move from this circulation to somewhat more like this over here, where your hotspot is now fixed to a particular latitude. So your substellar point is still going around the planet, but the hotspot is now localized. And if you compare this is asynchronous, so your green line is still going around the planet, and the black line is more thicker over here, it's overlapped, so you cannot see the planet. And this is because if you think intuitively, this is the star, this is the planet, and the star goes to its maximum. One of the faces of the planet is irradiated, and then when it goes to the minimum, it turns around. And then again, the same face receives maximal irradiation, and the opposite face receives minimal irradiation, which gives rise to this phenomenon. And if you now change these frequencies slightly, what you see is that this hotspot, which was then fixed to the surface of the planet, starts moving really slowly. So previously it was just a particular latitude, now it starts moving slowly. And if the frequency is given by the beat frequency, which is the difference between the installation and it's, the direction of motion depends on which of these frequencies is higher. So it will go from west to east or east to west, as you can see over here. And this is kind of an example of climate variability circumbinary planets. So previous research said that okay, circumbinary planets are as good as the single star case. Does not really hold when this beating phenomenon occurs. Now we will go on towards some thoughts about habitability of these planets. So the terminator is line, which separates the day side from the night side. For a synchronous planet, the terminator is fixed because the day side is always being irradiated, the night side is not. And for an asynchronous planet, the terminator keeps moving along with the day side or the substellar point. So we can define a new term, which is called a therminator, which is the hot and cold divide. This did not exist in literature before, so I took the liberty. Synchronous planets, terminators would overlap terminators because the day-night divide and hot-cold divide are just the same. Right? And both of them are fixed. For asynchronous planets, again, they would overlap, but they would just keep moving. So the hot-cold and the day-night divides keep moving along with the substellar point. But when this resonance occurs, the terminators become fixed. So even on an asynchronous planet, you would have a hot side and cold side. So the terminators are fixed, but the terminator keeps moving just as it used to, just as it is supposed to do on asynchronous planets. And when beating occurs, they both move, but they do not move at the same rate. This is important and interesting because people have talked about terminator habitability for these kind of planets, but the terminator does not receive alternating day-night cycles. And alternating day-night cycle is good for development of photosynthetic capacity, even since of other life promoting features of the planets. So these are planets where you could potentially day-night cycles even on. And here we can also think about circumbinary habitable zones. So this is the traditional habitable zone. If you put a planet here, it is too cold. But if it is heating, then one side of the planet is hot. So that side can sustain liquid water. Similarly, on the inner side, the cold side of the planet would be warm enough to sustain liquid water and hence make extensions to what our traditional idea of what's there. And coming to the dynamics part a bit, so we are able to find criteria that relate to the shallow water model, based on which we can differentiate between whether the planet is going to show beating or not. And it's a ratio of time scales, which is popular in literature, which is one of them is the time scale over the rotational time scale, and the other one is the wave time scale, which is the speed at which any perturbation on the surface of the planet can be distributed all over the surface. Based on these two time scale ratios, we can give an idea of. So if we calculate these for any planet, we can say whether or not they will show beating. And based on this criteria, we classified Kepler and TESS circumbinary planets and saw that two of these planets, the TESS planet and the other one, Kepler, they are most likely to show some kind of climate variability, which might be interesting to probe in using observational techniques. So at the end, climate of circumbinary planets can differ significantly from the equivalent single star case. Insulated diurnal residents can lead planets, asynchronous planets to behave like synchronous planets, and offsets from this resonance can lead to longer time variability with moving hotspots. This could have huge interesting implications for habitability of these planets. And finally, there are 2 planets which can be probably destined for this phenomenon. I really want to thank Marta for having me the opportunity to discuss a lot of this project with her, and also Dan Thomasek from Oxford University. And this was published last month. That's all. Thank you so much for listening.
Questions? Yes, no.
Great job. Thank you. That's a great question. Thank you. So what I think is that things that lead to resonance or non-resonance scenarios. For example, I think there's some work on why Venus is not synchronously rotating, and it was done by Deepayan. So I think it would be interesting to probe whether these kind of resonance scenarios can occur on different planets based on interaction of thermal tides and other type phenomena, and bring in the words resonant, but there's no why this resonance could not occur. This is completely theoretical. Thank you.
Other questions? All right, well, are there additional kinds of variable irradiation that you're planning on thinking about next?
Yeah, I mean, the next part would be to look at synchronous planets, actually. So this was just, I started working on this because I had to submit an abstract for a conference, and then I came up with this. And then now the goal is to do more theoretical work on this, and look at synchronous planets and how variable irradiation can synchronous planets. Those might be more detectable because those are more data for them.
Yes,
I can ask one. So I think it's very rare for reference to single paper. If you can share some of the experience or tips, and also if this is your first paper, and then how you come up with the idea, and then it's all like so. I mean, some knowledge are
Okay.
Okay. But if you can share some of
Thank you. That's something I actually wanted. I had a slide on that initially. But this is my second paper. The first paper is on Mariana application on stars. This I started working on because I wanted to go into exoplanets, and I was looking for different projects that could be done. I used the nebulous, which is on the slide, but it is a very easily adaptable code, and I used an already written code to modify it to apply it to the scenario. And then but once I found the repeating phenomena, I just ran multiple simulations to see if this works out, and then discussed with Marta. And finally talked to Dad. Kristen, my supervisor, he put me in touch with Dad because he's more like a theory guy. I had everything written in the first place, but it took a lot of more polishing, which came from both these people. It's a fun experience. Yeah, because I guess that's it.
Okay, well, let's thank Deepayan again.